Guys, in the last video, we talked about the basics of the agarose gel and the electrophoresis chamber, but we didn't really talk about what the lab is going to do. And I told you that's because we had to do that preemptive talk in order to talk about what this lab is doing. All right, so if you pull up the lab directions, what you're going to see is that you're going to be injecting multiple DNA samples into an agarose gel. And that agarose gel you will have to make. And that agarose gel also requires a buffer, and you will have to make that buffer. That buffer is going to come to you at 50 times concentration, and they're going to ask you to dilute it down to 1 times concentration, right? This is another word to say, for biology people, that this buffer is super concentrated. Think of this as molarity, okay? And this buffer is too concentrated for us to use, but we're going to make it this way so that way we can ship it to you pre-made, and it's probably a little bit cheaper to do that and let you weaken it down, because if we sent you the whole thing, you're going to pay tons in shipping in order to get it there, and you'll be shipping basically water, and that's it. So this 50 times concentration, do not let it throw you off, all right? Basically, the only thing that they're doing is using an MV-MV equation. And they're saying, hey, I've got a 50 times buffer, so I'll put 50 there. How much of that buffer do I need? Maybe in order to make a 1 times concentration, and I want to make maybe 500 milliliters of that solution. That's it, folks. That's all you've got to do. You've done it over and over and over. The only difference is that this X is there. Treat that like a concentration. That's it. Plug it into the dilution equation just like always. Solve for X just like always. You'll get the right answer every single time, I promise. As long as you put it in the calculator the right way. So you're going to take these DNA samples. The DNA sample is going to come from mother number 1, and then there is a mother number 2, and then there's actually a boy 1, and a boy 2, and then there's going to be a father, just one father that has been identified. All right, so one father, because we're pretty sure that this is the father of the child, okay? So we have a DNA banding that will happen from him. And then we have a mother, and that mother we need to pair up to one of the boys. So the mother will have her own DNA banding that will go through, and this mother will have a different DNA banding that will go through. And the 2 boys, of course, will also have their own DNA banding that will go through. And it's up to us to figure out, number 1, I have boy 1. Is he the father to that child? And then which one of the mothers goes along with that boy? And then I need to take a look at the DNA banding for boy number 2. And I need to look at boy 2 and say, all right, is that the father of that child as well? Yes or no? And out of the 2 choices with the mother, which one is the mother to that child? It could be the same. Maybe these 2 women that we have in question, maybe mother 1 isn't the mother of any of the children that we're analyzing. That's up to us to figure out. So what you're seeing on the screen right now is the laboratory document that we will have for you in our laboratory when you get to that point, all right? So in this lab document, it's going to go through a little bit of background, and it's going to go through maybe some things that you should know and review before you get turned loose in the laboratory and pretend like you know what you're doing when you really don't know what you're doing, and ruin everything that's going to come your way, okay? So here's the background information. I'm just going to take a few minutes and kind of read it and give you some of that back knowledge that makes this laboratory make sense a little bit more. All right. So it says, in a war-torn country, 2 young boys were separated from their parents, who had been imprisoned by the regime. The children were cousins who were born 2 months apart and looked very similar. And their mothers were half-sisters who shared a common mother. I know, family tree stuff, right? How complicated can it get? It says after several years, the regime was overthrown and replaced by a new government that released all political prisoners from prison. The prisoners were reinstated in their respective communities, and all charges against them were dropped. So during the period, the two boys had not been separated from each other. They've always stayed together, and they had been adopted by a high-ranking military officer who had no children of his own. Both the officer and his wife died in a liberation uprising, and for a short period of time the boys were placed into an orphanage. But when they turned 18, the boys were released from the orphanage, and they immediately began to look for their real mother and father. The brothers contacted a number of elders from their village. The elders informed them that after their biological parents were released, one of the fathers was assassinated. The second father was found to be in a village suffering from amnesia. Go figure, right? And two women who were thought to be their biological mothers were in a rehabilitation facility that housed 200 women. And upon arrival to the center, it was very obvious that the patients had not received proper medical attention. Based on the age and appearance, 10 women fit the profile for the two mothers. All right, so up here, you see a flow diagram. And the flow diagram, here's Grandma. And Grandma gives birth to two girls, Mother 1 and Mother 2. Now remember, they said that those two women were half-sisters. So they had different fathers. So it looks like Mother 1 was married and had a child, and Mother 2 was also married and had a child. And it's these two children, the cousins. I know it says the brothers here, but that should be cousins. That was a mistake in their write-up. So these cousins want to figure out whose mother is who. And in the directions it says that this father is now dead. We know that that father's dead, no longer living, but we have this other father that's out there, and we need to figure out that father, which child does it go to? Does it go to this one, or does that father really go to this one over here? So you're matching the children up to their respective mother, and then you're figuring out this father that's still living. Whose father is it really? Child 1 or child 2? So there's kind of your family tree. All right, so they give you more lead up to this, right? And they say, listen, we had this facility. This facility housed 200 women in total. And 200 women is quite a bit, right? So we need to narrow this down. And they narrowed it down to 10. Right there it says 10 women fit the profile. But out of these 10, how do we narrow it down even more? So what they decided to do was compare the mitochondria DNA. So your mitochondria actually comes from your mother. The sperm carries very little mitochondria at all. So all the mitochondrial typically came from your mother's side. And this mitochondria has DNA that's associated with it. And what they did is that they compared the mitochondrial DNA of the boys to the women. And they were able to take these 10 women and basically boil it down to 2 possibilities that were really, really close. But mitochondrial DNA is not perfect. It only gives you really one side of the lineage. because your DNA is made up of your mother and your father. So mitochondrial DNA does a very good job on the mother's side of the house. But when you want to involve your father, that's not going to work for you, and it's not going to give you a full picture by all means. And this mitochondrial DNA now has to be changed into something that we call chromosomal DNA. And this is your real DNA that comes from your parents. Half of it on your mother's and half of it on your father's. These changes that begin to happen, because you have maybe a brother or a sister, you don't look identical. You're not made the same way, right? There's differences between you. Well, these differences are going to be called the polymorphisms. And that's because the DNA fragment is different. The strand is different. The fragmentation pattern is going to be different. And these are polymorphisms that happen because of that. And these are what we analyze in the electrophoresis gel. All right, so the directions are going to walk me through a couple of things that I need to do. Number one, it says prepare an agarose gel in a casting tray. So I'm going to heat this agarose up, get it warm, 60 degrees. I'm going to pour it into the tray, and I'm going to let it jelly on me. And you can see the comb here that they've placed there towards you in the diagram. And then we're going to remove the comb, and then we submerge that entire gel in the electrophoresis chamber. The next step, we're going to give you a sample of DNA, mother 1, mother 2, child 1, child 2, and father. And you're going to puncture the wells, or this foil, with a micropipetter tip, and you're going to suck up that sample in the micropipetter tip. You're then going to carefully deliver those samples into the wells of the agarose gel. Notice where they have positioned the comb. The wells are over here to the left because that's the closest side to the negative, which is the black cord. And the feet of the gels, there's actually two of them here. Here's maybe one gel that one person will make, and here's another gel that a second person will make. You can run two at the same time, no big deal. But the feet of the gels are pointed to the positive end, which is the red cord. It has to go that way, or you're going to ruin it. Okay, I'm going to repeat it. It has to be positioned in that way in order for you to get data. It's probably one of the most important things that you need to remember in electrophoresis. The feet of the gels have to be pointed toward the end with the red cord. That is your positive side. Number 4, we're going to put the cover on it, and then these cords get hooked up to a power supply that will start creating the voltage. And then as this gel begins to develop, this maybe is something that you would see. Now, it's just an example. It's probably not going to be identical. It's just an example of what you'll see here. But we're only looking at colors. We're not actually looking at real DNA banding because this is an intro lab, remember? So they're going to make it easy. They're going to put colors and dyes into these samples, and we're going to compare the dye color that shows up in all of these to figure out which one is which. All right? So here I see a sample. That looks blue. That looks red. That looks kind of blackish, purplish. This one looks orangey. That, of course, is completely different than that DNA sample. That's completely different than that one. It's completely different than that one, different than that one. And this one, well, I see a blue here and a blue there. This one I see a red here, but that also is different than all of the others. All right? So there's what we call the banding pattern. Here's directions on how to make the agarose gel in order to start this process. So here's your recipe to make your buffer. Add your agarose in, nuke it, let it cool to 60, and then put the casting tray feet and comb in and pour your agarose on the inside once it cools down to 60 degrees. Okay. It also says wait 20 minutes. That's about average of what it takes for this agarose gel to get jello-like on you. So 20 minutes, give or take a little bit, that's when your cake will be ready to take out of the oven. It also gives you a table here, individual 0.8% gels. It basically gives you a recipe. If you are using the newer gel electrophoresis that we have, you have a 7x7 tray. If you are using some of the older ones, you probably have a 7x10 tray. So use the proper recipe here. It tells you how much concentrated buffer to measure out. It tells you how much water to add, and then it tells you how much agarose to add gram-wise. Notice these are super tiny amounts. Volumes can be micropipetted, and your grams of agarose are also super tiny. It's not going to take a lot at all for it to do its job. The gel electrophoresis, this is maybe a better picture of what's going to go on. This gives you the side of the chamber. Your gel and your casting tray actually goes down inside of the chamber, and then you will load your samples into the wells, and then you'll place your cover on it, and you'll connect it to the voltage. The key code is tube A is going to be just standard markers. So all of the colored dyes will be into tube A slot. Into tube B, that will be your mother 1. Tube C will be mother 2. Tube D will be boy 1. Tube E will be boy 2. And tube F will be the father. In order to make the buffer for your electrophoresis chamber, they also give you the directions here. So look at, this is the Edvotech models. We do not use the Edvotech models for our gel analysis. So just go by total volume required. Just kind of eyeball it and estimate it. Pick out one of the milliliters that you need to make, and it will tell you how to make that buffer with the recipe straight out. No calculations on your end will be required for that. Next is the voltage. You have a couple of different voltage choices. Not all power supplies will give you these voltage choices. Some are very standard, and you only have one or two options, and that's it. But notice the higher the voltage, the quicker the things will run through the gel, because at 125 volts, we get 20 minutes, and at 50 volts, we get 90. You probably are saying, well, why doesn't everyone use 125? And the reason is because your separation might not happen as well if you rush everything through the gel, okay? And then maybe not everyone has an hour and a half to wait on a gel electrophoresis to produce. So that's why not everyone uses 50 volts. So kind of just eyeball it in the middle. You'll very often see people use 70, 80, 90, somewhere in that range for their electrophoresis chambers. But that's why you do have an option. It really depends on how complicated your sample is going to be when you begin to do this. All right. As far as the post-lab questions here, do not worry about these. If I want you to answer these, they will be in the post-lab document with the other questions and stuff that you need to do that comes along with the lab. All right. So there's an overview of the lab experiment. Now let me go back to here. Now that we kind of fully understand what's happening, hopefully, we now know that there is a chance that boy 1 will band out maybe this way. Okay, they're going to be colors. They won't be lines like this, but this gives you an idea. And then we're going to take a look at mother 1 maybe, and then we'll take a look at father. If boy 1 is the child of this mother and this father, boy 1 will not have an identical replica of either one of these. But half of it might come from the mother's side, the other half might come from the father's side, and maybe this one down here is also the mother. What I'm doing is I'm comparing the bands of that particular boy. And it looks like this band matches to mother 1, This band matches to mother 1. This one matches to the father. That one matches to the father. And this one matches to mother 1. It looks like all of the bands that this boy has, part of them are coming from this mother, and the other part are coming from this father. So I feel a very strong relationship that mother 1 and father has come together to make this boy in the past. Right? I feel pretty good about that. Statistics maybe is probably on my side. But if I had mother 2, I'm just going to label this one as M2. She will have a different banding pattern. Even though they were half sisters, she will have a different banding pattern. So this boy 1 has a mark here. Notice that mother does not. That's a good sign that she's not really the true mother, if there's other things that come along that aren't matching. That band matches here. Well, she didn't have it. This band matches that one. That's okay. But here, it could have came from the father, but that one could have also came from the mother. We just don't know. And then this one, yeah, it looks like it came from here, and it looks like it came from here possibly. But this mother does not match perfectly with this boy. This mother matches much, much better. This one's a dead match. This one's a dead match. These two probably came from the father. This one came from that mother. And that is how we determine which parent is who. All right? Except in your case, you'll be looking at colored splotches. Again, it's an intro. Bear with us. These things will get more and more real as time goes on. But in the beginning, we just want you to focus on the chamber, the casting tray, making a gel, loading a sample, and just a quick analysis of what we're seeing on our gel electrophoresis. Be sure to take a picture of this gel. You will need to upload it into the Blackboard system when that comes around. So do not lose it. That will be a required post-lab question, quote unquote, that will come along. So good luck with the gel electrophoresis. I think that you'll be okay. It's, again, a little bit different than what we've been doing so far in the program. This is more biology-based. It's more biotechnology-based rather than strict chemistry and equipment and solution prep. All right, so good luck. If you've got questions, you know how to get a hold of me, and I'll see you in the lab.